Oh, I should change what we're doing. Just make that note here. Zero dot 16.0. Okay. All right. I think that's everything in order. We can get started with the stream. Okay. Welcome to the stream today. I'm just going to be working on upgrading. I'm really focused on upgrading to 0.16 of Zig, the newest version of the Zig compiler. I've already got some things done. I've migrated to the juicy init, which has been helpful. It's actually helped in being able to get rid of some code because I did a lot of code that handled transforming environment variables that I don't need to do anymore. So that's helpful. Okay, I'm going to continue on. Okay, now needs to take an IO parameter. This is unfortunate. You know, for now, I'm going to turn this into a panic. I don't want to deal with having IO in this. Because eventually I want to fix so I'm going to put like should handle more. Okay. Const init. Yeah. And okay, FS has no file. And we're gonna probably, I'm gonna guess, need an IO here, but we'll get there when we get there. Okay. Member function expected 2 arguments found 1. Yep, need the IO here. That needs to go up here. See, no field or member function named seek2 in io.file. Really? They get rid of seek2? Okay. Seek2, file seek2, file seek by, file seek from int is to IO file reader seek2. Okay. file reader. So really we need to change the reader to be seek2. And again here, reader. Okay. Wait, what's R and what's reader? Okay. Says root source file struct standard has no member IO. It's true, it does not. FIRI. What's this one called? Really, is that it? Zig build. Doesn't like the formatting, but I don't know why. If I do Zig format, Zig format source. See, libs tracer. Do it without check. Let's just run it. Okay. Interesting. Okay, we got the line number program. I think we're back to where we were. I have upgraded to 0.16, so I guess we just start working on the back on the line number program. That wasn't so bad. I didn't think it was going to be bad because I don't really use a lot of IO right now. I mean, I read in the files that I need to at the beginning, and then I just kind of use them. And so really the big change was last time for me for switching to using the readers, which was super helpful, actually. So let's see, we'll want to open up the line number program. Oh, I need to upgrade ZLS. Let's do that real quick. ZLS. Let's see, local bin rmzls widget. Let's see, tar xvjf zls. ZLS is open. Okay. And that. And let's see, we want what do we want? I wanted line number program. Okay. And I wanted what else do you want? Probably want main. Oh, we know to commit all this. That's for sure. Commit, and CC chore upgrade to 0.16.0. All right, so now what is next? I think where I got into is in the line reader. Yes, I need to do something with vendor specific codes. There. So I'm getting an advanced extended code that I'm not checking because something. We need to check that for sure. We're getting this panic here. I BDB, see, Zig out, then BDB, Zig out, then test. Yeah, I get. Red, check me. Line count 0, 1, line count 2, format 0xb. And then I get this panic. Oh, excuse me. Let's solve that problem. Mm-hmm. Excuse me. Let's do log.debug opcode. And we need to make our logger const log equals standard.debug dot no standard dot log no standard dot log dot scoped. This is scope 2 line number program. Code 0x9. Okay. That bigger there. All right, let's see what we got here. Standard out codes. I think we need to go to, well, we'll take a look here. Standard out codes. Etc. Line number standard opcodes are 1, 2, 3, 4, 5, 6, 7, 8, 9. So actually, this should be a standard opcode, right? Not an extended opcode. Let's go check here. If opcode, okay, let's do some logging here. Opcode log.debug. Nine to 0x009. So if opcode is greater than header opcode base, let's log debug header header so header, we've got unit length, version, address size, select a header length, min instruction, max ops, default is statement, line base is -5, line range is 14, opcode base is 13. Okay. So if opcode is greater than or equal to opcode base, advanced special opcode, we don't do that. Or extended opcodes. Standard opcodes are here. The address. Are there only 2 extended opcodes? Okay, so this is a version 5. Okay, yeah, there's a third one. Okay. Maybe I was missing a page here. Yeah. Extended opcodes shouldn't have this value. So sure, an extended opcode is being called when it shouldn't be. If opcode is 0, take this advanced extended opcode. Okay, and that is what I see. We get 0. It's the opcode. Let's make sure that's correct. Hmm. Standard opcodes. Line number program reference file name sequence is 0. Okay, so let's see. Maybe I'm header. State machine stuff. Okay, line number information generated compile unit. Okay. This is probably what it is. These have a multi-byte format. The first byte is 0. The next bytes are an unsigned LEB 128 integer, giving the number of bytes in the instruction itself, which does not include the first 0 byte or the size. The remaining bytes are the instruction itself. Okay. Here's our problem. So we get the 0 byte. If opcode is 0, then we do this. But to advance special opcode, what we need to do is not do this. This const length, let's see, count bytes inst bytes. Let's see, read uleb dwarf read uleb 128. Let's see. U64. I was reading the wrong one. These are multi-byte. First byte is 0. The next bytes are an unsigned number, giving the number of bytes in the instruction itself. Remaining bytes are the instruction itself, which begins with U by extended opcode. Okay. R, I believe. And what's the next C? That's it. And use local constant, yes. And then opcode takes that, and then we do now we got to okay. Let's see. Mark this as mark B. Okay. Let's see. Extended opcodes. Here we are, extend opcodes. Mark C. Okay. So in-sequence opcode takes no operands. It sets the in-sequence register of the state machine to true and appends a row to the matrix using the current value of the state machine registers. Then it meets the registers to the initial, resets the registers initial values. So set line address takes a single relocatable address as an operand. The size of the operand is the size of an address on the target machine. Takes a single parameter, an unsigned 128-bit integer. It sets the discriminator register. So I'm going to say this number is pretty useless, except maybe in here, we just read a bunch of ulebs. I think maybe here we do like instead. Like r dot read, or was it like, what is the word? Is it it's not take, it's toss. And we want to toss how many bytes? We want to toss count -1. We just do that. Let's see, doesn't like expected, invalid, found in a stream. Okay. Okay. That's working. Opcode 0, opcode 4. And we get invalid standard opcode. Oof, invalid enum value. It's on line 111, 111. Let's do this. These have U by opcode filled with as many field which may be followed by 0 or more leb 128 operands. Opcode implies the number of operands and their meanings, but this line number program header also specifies number of operands for each standard opcode. Okay, so I think what we need to do is standard opcode should take the opcode. This is what is it? GW dot LN LNS, I believe. Enum from int. Okay. Another check me here. But now reading more opcodes. That's good. So 0, 0. So what we need to know is actually go to extended opcode and take a look at what the extended opcode is. So we're going to take a look at that. Standard.debug, or no, log.debug. Extended opcode. Zero. That would be a problem. Because I don't believe 0 is a valid extended opcode value. No, it is not. Now the question is, why is it parsing it wrong? Chili. Let's see. Log.debug. I want to know every time we read this. I know. Reader state. I don't know where we're at in the reader. Offset. What's it called? It's called seek. It is. No. How many bytes we are off there? Seek. B. Okay. Where's the reader coming from? Line reader. Okay. That's just the line offset. Okay. Section reader, sections, that line offset. So we need to know what the line offset, debug line offset. We already got that there. Okay. I actually like this format too. Let's see. $91. We're offsetting 970 into the debug lines. Okay. Format, and then we're going another 0x5b. Okay. So if I do something like what is it? I want to see debug lines. Or is it read elf? Read elf is I think I want. Read elf dash help. Dash W equals dash W L. Zig out bin. Test bin, right? No, VDB. Yeah, test bin. Yes, debug line. Line number statements. 38. Let's do this. WL read elf obj dump. Is it read elf sections? Read elf sections. Dash S, and we want to zig out bin test bin. And I want to debug lines. So I got to jump here. Okay. So hex dump. Hex dump that. And we want to hex dump what? Bunch of undefined values here, huh? Let's dash C. Yeah, I want to hex dump dash C. Okay, there we go. A bunch of undefined. We need to skip 3CA. Okay, 3CA. Let's just do the math here. 0x plus 0x3CA. B3803. Okay. A03. We need to go 3B. Or no, we want to go 5B. B3A5E. Undefined. Every time. Oh, because I'm doing size, not the offset. Ugh, that makes more sense. This is the offset. Okay. All right. This is the offset here. That's where we want to be. Right. Yeah, it is zeros, a bunch of zeros. Let's back it off a bit. Let's go to where we start counting this. Okay. So we are here, big debug line offset. We're at the beginning there. So we should see a bunch of information regarding the header of this debug line program. So let's take a look. I'm gonna sneeze. Oh man. Let's see. Skips down past the header. See format, attribute, language, form. feel like the header would be debug line. Line number header. Should be the beginning if I'm right here. Debug line header. Let's see. Yeah, line offsets. So we start here, we get the line reader. Oh, hey. How's it going? Should I torture myself into learning how to use Vim? Well, I wouldn't torture yourself for that, but I think Vim is quite nice. Okay. So reading in here, and we take the CUINT length 64-bit, pointer size, be 32-bit. All right, so here's the first int we read. We read the first 2 bytes as the length of the line number program. Okay. If we look at unit length 334356, 141A. I don't think that line number length makes sense. 0x141A decimal. Yeah, 5,146. This doesn't make any sense. It's saying the unit length is way bigger than it really is. Right? Header. One four one A, unless it's like 1A 14. Is this big Indian? Oh, it is little Indian, and I just wrote it backwards. 6676. Still not right. Something's wrong. This header. Unless I'm reading things wrong. Oh, these are the first ints. Yeah, read it. 64-bit or 32-bit. Okay, there we go. So we need to read a 32-bit length value. So this is it. Be 0050551A. We need to add a 5 in front of there. Oh, 5 1. Jeez Louise. There we go. Okay, 334356. That is correct. Okay. Everything is right there. What's Zig? Zig's a programming language. So I'm working on a debugger for it. Okay, that's right. Then it should version 5. Version 5. Address size 8. I don't even think that would be. Yep, address size is 8. This is another 16. No, that's just a byte. So then the next thing we read is dwarf version. Read address size and segment selector size. Segment selector size should be 0 then. Segment selector size is 0. Header length 44. 2C, that seems about right for 44. 20 would be 1632 plus another 12 would be, yeah, there you go, 44. That's right. And then how much do we read for 44? 44 is 1 byte. And then we take in header length. Wait, no, header length, U64. Reading int of 4 bytes. Okay. So read these 4 bytes. And then we get 0, 1, 0, 1, 0, 1. 1, 1, true. 1, 1, true. FB, which would be -5, line base. Let's see. Take 1, take 1, take 1. Line base should be take 1 as well. I8. By FB. I think that would be -5. Yeah. B, C, C, D, E, F. B, C, D, E, F, F. Equal 5. Should be. Yep. That seems right. Okay. We take all these in. Reading now a 16-bit. No, I'm wrong spot here. Read range. We take 1 more. 1, 2, 3, 4, 5 bytes after the header length. 1, 2, 3, 4, 5 bytes E. Okay, so we should get a, is that 14? Line range is 14, and the last should be opcode base, which is 13. Which is that, which we should then get a D. Yep, maybe C, D. Yep, there we go. Okay. So then this is the line number program starting here. Nice. Zig is a programming language, ziglang.org. Here's the programming language. You can download it. Here, just 0.16.0 was just released this last week. And I just finished upgrading my debugger to 0.16.0. And now I'm working on working on the debugger. Okay. So here we see the offset is 59 bytes. Well, that is not true at all. Right? Oh, wait, because then once we get the opcode base, excuse me, once we read this, we have to read the directories and everything. That's just the beginning part of the header. Oh man. So then we read that. Hey, you have a good night too. Let's see, line header. So yeah, then we read the line reader to get the DIRs. We know that the header length is 44. I go back to here and we look at the line number information. Header. Header length, the number of bytes following the header length field to the beginning of the first byte of the line number program itself. Okay, so this is what I want to see, because this will tell us where to start in this hex output. So first we need to find where the header length is. That would be 44, which is right here. And so we need to go from there, 44 bytes. That is, from here, 44 bytes is going to be, let's see, 16, 32, then another 12 bytes. So that'd be, let's see, 13, rather, 16, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44. Perfect. And that looks right. 0, 0, 9. Okay, so this is the beginning of the line number program right there. So far, everything's coming out what I expect it to. A line. Read out the header. We get the opcode. And we get the, yeah, advanced opcodes. So I'm guessing that either 0, because yeah, get an opcode of 0 and extend opcode of 0. So what marks the end of the line number program actually? That's a question. So state machine instructions in a line number program belong to one of 3 categories: special opcodes, standard opcodes, and extended opcodes. So we have the header, and then we get the program, standard content, description. Okay, as stated before, the goal of line number program is to build a matrix. All special opcodes do those 7 things. Special opcode is calculated this way. Standard opcodes are applied this way. You get the extended opcodes and it just ends. So I'm guessing that just read until you get to the end of the length of the program. This program's like 300 kilobytes long. Okay. I wonder. Let's go back here. We get 0, then 9. Or then 2. Sorry. We get then 2. Then we get opcode 4. Which is right here. Opcode 2 is set address. Okay, and so when we set the address, we do consume those 8. Header.address size is 8. Then as U88, else as U84. The address size should be 8. So that makes sense that we read 9. So we set the address size. Okay. Boom. 1, 2, 3, 4, 5, 6, 7, 8. Then we get 4. 4. Then we get 5. Then we get 13. And then A. 5. 8, 4. 5, 9. 0, B. 74. 6. 5. 5, 9. 0. Okay, we get 0. And we get to extend opcode 1. That opcode we say is length is 1 and 1. Okay, then we get another extend opcode 0. Length is BE. Oh. Get 0. Extend opcode length of 1. Here it is. So we should get 0 right here and then BE. But instead, we read too many. So we skip to here. Right there, something's happening wrong with the way we interpret that line. This is 0, 1, 0, 5, 6. And that is about right. 5, 6. See B, C, D, E, F, G. That's 5. Plus 6. 1, 2, 3, 4, 5, 6. Oh, wait, we interpret the length. What is the length of this opcode? BEB3 14. Interesting. I wonder what the length of this opcode is. Okay, let's take a look at this. Let's read when we do the lengths of the opcode. Let's see, count, let's see. Log.debug debug RB extended opcode instruction count. D or D. Yeah. Very long count. And then we get 0 as the opcode. Wonder what that means. Why do we have a whole bunch of blanks in our opcodes? Five B, huh? 1, 2, 3, 4, 5, 6, 7. Wait. 4, 5. 5, okay. And then B. 1, 2, 3, 4, 5, 6, 9, 10. A, B. Right. 8, 9, 10, B, C, A, B, C, D, E, F. Oh, this is 0. 7, 8, 9, A, B. Must be opcode, and so that's pointing here. Opcode is 0. Tells me something's wrong. First byte is 0. The next bytes are an unsigned LEB 120 integer giving the number of bytes in the instruction itself. Okay. Let's go back and look at our standard instruction here. We agreed that the beginning of the thing was 44 bytes after this, or 2C. So go 1, 2, A, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. So this is the beginning. Yep, 0. Then we go 9 more, which takes us to 1, 1, 2, 3, 4, 5, 8. Then we get 4. 4 is, let's go to standard opcodes. 1, 2, 3, 4. Takes a single unsigned LEB 120 operand and stores it in the file register of the state machine. Okay. So first thing we're doing is after we set the address, we set the file number. Okay. 5. We set the column. The column takes a single leb 128 operand. 1, 5. Let's make sure that that matches. Yep, 5, 1, 5. And we're going to set the column, the state machine. Then 13. 13 is the first non-standard opcode or special opcode. Add assigned integer. Special opcode does this by taking the opcode. Opcode minus opcode base, 13. Opcode base is 13, right? So 0. Just opcode divided by line range. Is there a 13th opcode? Let's say I believe 13, yeah. Oh. So then get 13 A. Okay. Do the A, which is another special opcode. Then we do 5. Just setting the column number again. 5 takes 14. Yep. Then we do 84, special opcode 59, special opcode 0B is, oh, 13. Yeah, this is hex 13. Oh, I'm an idiot. So yeah, 0B is not. 0B is that is 12, or no, 11. So that is set epilogue begin. So we set this takes no operands. Okay. And then we get 74. That's special opcode 06. That is a standard opcode negate statement. Negate takes no operands. Okay, 5 takes an operand of 1. We do 5, 9. That's a special one. Then we get into extended opcode 0. The instruction count is 1. The opcode is 1. And that is where we're right here. Okay. And then we get the length BE B314. BE, B does have the extended, yep. That's what? That's BE. It's going to be 1, 0, 1, 1. So 0 and 1, 1, 1, 1, 0. Okay. And then again, 3, and then 1, 4, 0, 0, 1, 4. Okay. You get a large number of bytes. Makes sense because the extended opcode is multi-byte format. The first byte is 0. The next bytes are an unsigned LEB 128-bit integer, giving the number of bytes in the instruction itself. It does not include the first 0 byte or the size. Okay. The remaining bytes are the instruction itself, which begins with the U-byte extended opcode. What is the value that I got there? From here, it says the value is 519BE. Okay. That's not, no, that's not enough. Saying this instruction is how many long? Is that the end? Is that just the end of it? 4270. Maybe that is the end. Right. A bunch of zeros. Interesting. It's possible. I don't know. Well, I'm gonna have to stop for right now, but I will see y'all next time. Thanks for watching.